Thank you. Many thanks for inviting me here. It's a honor to participate, and so I will try to describe some mathematical landscapes, and use. I'll try to mention many, if not all, of the parts there, are related to Michel's work, and some wouldn't exist if not for Michel's work. But yeah, unfortunately, the description I'm able to give is nowhere reaching the clarity and depth of Michel's papers, but we can only dream of that. Okay, in any case, so it's so the main thing that I want to explain is joined with Ivan Lossev, but based on all the works with first of all with Noncommutative, and I mean still so it's in progress, and then it's somewhere in progress, and also with some published work to Anno and Mirkovich. Okay, and so the main story I want to talk about is something rather concrete and specific, but I want to start with a general picture from motivation, and this is and I will I maybe will be very vague and descriptive, because if I want to go into full details, it may take the whole hour. But in any case, we start with the context of so this is a symplectic resolution. So X omega is algebraically symplectic. And yes, pi is the resolution of singularities, and the important thing is that there is a action of the multiplicative group. Well, just for simplicity of notation, we can think it's over C, and then there is an action of the multiplicative group dilating the form. And it contracts, contracting y to the point. So y is affine in particular. And so typically in most examples I know, typically d is equal to 2. So there may exist another singularity. Another such resolution of the same y. So pi prime from x prime to the same y. And by the general, by the conjecture, so Kawamata and Bondel-Orlov conjecture, which known as K equivalence implies D equivalence. Since x and x prime are easily seen to be Crepant resolutions, so one expects that dB of cohex is equivalent to dB of cohex prime. And so in this case, So in our case, it has been proved by Kaledian developing a method from our joint paper. And in a special case in our joint work, I mean, first, in a special case, which I will not, for quotient singularities, well, by myself and him. But the way it's done by relating both by relating both dB cohex and dB cohex prime to dB coh, well, dB of like maybe A mod, where A is a non-commutative Coherent resolution in the sense of Michel. Yeah. And so basically what and so this A is constructed by quantization in positive characteristic. Which I will not describe in detail. Maybe I'll just want to say that when X happens to be the cotangent bundle to homogeneous projective space, then this is closely related to study, well, description of the vector bundle on Gmod P, which is just direct image of a line bundle. For example, a structure sheaf on under Frobenius, and this is so for Grossmanian, maybe Grossmanian 2n. There's a comprehensive study by Michel and Spelva and the collaborator whose name I am trying to learn to spell. So my Vandenberg and okay, sorry, Raid Shelders, right? Okay, so this is just a side remark. So yeah, instead of yeah, as they say, yeah, the point here is that just stare. I mean, they've been doing for many years, trying to stare at this construction and make it into a more precise picture. And so looking closer at this construction, we kind of get a more precise picture. In particular, we say that so this K implies D thing, it just says the equivalent. It doesn't say the canonical equivalent, and maybe on physical grounds, one expects that something along the lines that there should be some space of parameters, and the equivalence depends on a path in the space of parameters. And this is what we can make more precise. And okay, I want to say pictures are 1,000 words, so I'll just draw a picture and so I'm just saying that this all fits in a local system of categories. On some vector space of parameters minus certain hyperplanes. So in a special case, this can be a configuration of affine root hyperplanes. And basically, so hyperplanes, rational hyperplanes. And this is some periodic configuration where, discrete and translation invariant and the translation of some lattice. So basically, if you remove these hyperplanes, there will be some, in the real locus, there will be some regions, and so which I call alcoves. And then in the complex domain, there will be some cones. And then in the point is that this maybe I should say it's VR plus IC. And so we have some local system of categories where on such a region we place dB of Coh X C. So what this means is that this cone in determines a resolution, so for which this is the positive Kähler cone, and the alcove determines in some way a non-commutative resolution. So here there's some A delta 1, and if when then we have a path connecting these two, we get a derived equivalence, and actually every point like that is connected by a straight path to a point like that. So they come with various derived equivalences. And yes, and I just say some features here. And so the first thing which is related to Tom's Bridgeland's stability condition, and so what we call real variation of stabilities. And this is a precise relation, well, a precise answer to the question, to the following question, that if we have different alcoves and we travel by some path from alcove to a neighboring alcove, well, we get some equivalence, but it is not exact. The billion hearts will be really different. So maybe it would rather draw it here. But it turns out that well, between abelian categories, or we can like if you fix X, we can identify all these triangulated categories, but then you can think about it in terms of different T structures on dB Coh X C. But anyway, between abelian categories, A delta and a delta prime. So it turns out that this that the equivalence corresponding to this path is a perverse equivalence with respect to some is perverse, and where the perversity for a filtration governed by the central charge. And then yeah, and then the important kind of feature that again is conjectures in general and proved in various cases is that monodromy. I mean, this is not so much monodromy, but if I action on K naught, so we have local system of categories, but action of phi 1 on K naught it can be related is equal to monodromy of a covariant quantum connection. And so, yeah, this I think relates to the work of Spell and Michel on GKZ, but again, I will not follow this thread. So, yeah. Okay, so so basically, these non-commutative resolutions, they often of interest in representation theory for representation theory. So for T star G mod B, these are just quotients of enveloping, and I will say what they are in the Hilbert scheme case. So we want to understand somehow their representations better, and the hope is so hope is to describe the classes of irreducible A delta modules in the K group of coherent sheaves on X as as canonical basis. And so this is realized, so known when X is equal to T star G mod P due to my work with Merkovich. And this should, yeah, this is in the sense of Kazdan-Lustig theory, but again, I will not give the precise definition, but this should reduce to the following conjecture that these A deltas, well, can be given a grading so as to become Kazul quadratic algebras. And the standard technique, so Kazdan-Lustig theory, like provides a pattern, so and give an ansatz for proving this. So gives an ansatz, and so we for doing this, So we should relate a delta to constructible category to a category of perverse sheaves. And okay, so I'll maybe say two more, well, particularly vague sentences. And I mean, maybe there I was vague for lack of time, and here I'm vague for also for lack of general understanding. And that, so yeah, so maybe in some cases this can be such a procedure is so this fits in like local in geometric Langlands patterns, Langlands equivalence. And another point is that, well, this perverse sheaves can be related to microlocal sheaves on the cotangent bundle, and thinking about it microlocally, and then relating microlocal sheaves to Fukaya category, and so this into homological mirror symmetry.
Only those parts of the Bezrukavnikov algebra, or is it conjecture that the full constructors with complex building conditions?
No, these are so this specific one. So it's basically there is a construction here which assigns us to structures and then algebras. Yeah. To. Okay. So so now I'm switch gears and I will try to explain something much more precise, but motivated by all this. So that X now, sorry, maybe I first say Y will be A2 and more the Sn. Maybe for good measure, I'll take A to N minus A to N minus 2 more Sn. In other words, it's a square of reflection representation. Or you can take configurations of endpoints on A2, but centered at 0. And X will be the Hilbert scheme of points on A2, and yes, it's just also center of mass at 0. So then there is a famous result of Bridgeland, King, and Reed. Sorry, it's no, I think it's theorem Heyman, but based on results of Bridgeland, King, and Reed. And so I guess that people refer to it as BKR equivalence because that's how Heyman calls it. But so dB co X, there's this equivalence with dB co Sn equivariant of A2 N minus 2. So this is this orbifold. And so this is something that Mark Heyman proved in the context of his work of non-factorial conjecture and work on McDonald polynomials. So we can think of this as, you know, a T structure on dV giving it. So we have a transporting methodological T structure here. We got a T structure on dB cohex. But in fact, this is a part of a more general story. So this fits in a more general story, which is a special case of the thing that I described vaguely. And so now V, well, in general, V is nothing but the Picard group of X, but here it will be just C, which is H2 of XC. And it contains VR, which is the real line. Now on this real line, I want to plot various points. And okay, so there's 0 somewhere, but the 0 is not one of the points I plot. But I plot so R, which is R, it contains, well, it's a collection of hyperplanes. Here, hyperplanes just points. And so this is the set of all fractions A over B, where, say, reduced fractions, and B is strictly larger than 1, but less local than N. Huh? Yeah, sorry, it contains. And so say for N equal to 3, we get what? We get 1/3 minus 1/3, 1/2. Well, maybe it's not to scale, maybe like that. And then 2/3. So these points, they obviously break R into intervals. And so like a component of the complement. Yeah, so this is something maybe S. So if I take R and remove S, well, this is this joint union of things like A over B, A prime over B prime, successive fractions of this sort. So I will call this an interval of stability. And so here is a theorem. So the theorem, I think, is essentially a special case of something much more general that we proved in a paper with Losif on Nightingale's conjectures, but well, in a forthcoming paper, we'll maybe discuss a special case in more detail. So theorem that to each interval of stability, one can assign one can AI. So this is a non-commutative resolution of Y, which comes with a derived equivalence of Y with GB of X identified with GB of A mod. So basically A only meaningful up to Morita equivalence. So well, think interchangeably of this data as, you can think of it as a ring, or you can think of this as a T structure in DB equal X. So this is this A mod part of tau I, a T structure on GB. So there are two so I will describe various properties. So maybe the first two characterizing properties is that for I equal to minus 1 over n, this is well, tau I is equal to Heyman structure. So in other words, AI is nothing but SN smash well, C of A turn minus 2. And one is that, so that's exactly this relation between things happening for neighboring alcoves. So this perverse equivalence story, which here I can say more precisely. So for each I, irreducible objects, irreducibles supported like at the 0 in Y, ion bijection with partitions of n, so which I will denote by lambda, and so say L lambda is irreducible, and then the relation between the relation between the T structures. So suppose we have like a point here, like A over B, and here we have an interval I, and here we have an interval I prime. Then, well, the equivalence the derived equivalence, built into what I've just said, is perverse, where the perversity function sends lambda to the following. So I need to write lambda as a mu plus b nu, where mu is b regular, so all parts, no parts divisible by b. And then lambda goes to something like b minus 1. So something like this. And there is also something, maybe I will not write it, but so we have perverse equivalences, then the irreducibles here and irreducibles here and in bijection, but this bijection is not compatible with labeling by partition. So there is some non-trivial permutation having to do with Molyneux involution, but let's not. I mean, there is some interesting combinatorial kind of aspect of this. And actually some open questions about that, but but I don't have relabeling by essentially well, Molyneux involution. Okay. So so those two properties characterize it, but I mean it's also everything is kind of equivariant for dilations, and so whatever happens at zero determines the rest. So these two properties with maybe some equivariance like that uniquely characterize it, but there are further properties. So first of all, each of these so this tau I is given by a tilting bundle like EI, where of course for initial interval this is this famous Procesi bundle, so generalized Procesi bundle. Sorry? Mu has no parts divisible by B. Four is, well, so that's just easy property. If so everything is obviously periodic with shift by one, so is tau I times of one, something like this. And yes, and five, well, I promised that I will say something about relation to representation theory. And so so consider prime P more than N, and let a so let HC be the rational Cherednik, rational double affine Hicke algebra. With parameter C, which I want to take to be an integer. And then there is some regularity condition that C mod P is not equal to any of these things A over B. B. Where A is less than B, less or equal than N. And so, and then if C over P, and suppose that C over P lies in I, then if I take HC modules with some condition on the sample character, then this is the same as AI modules. Well, supported at zero. So basically, the bottom line is that these algebras essentially are Moret equivalent to Cherednik algebras in positive characteristic. And there should be a similar statement with OVC with Cherednik algebra to root of unity, but I like this better. Okay, so so that's, I mean, very kind of maybe just one example, quick example, and then I pass to constructible realization, still partly conjectural, unfortunately. So example is consider I to be like, well, the next interval after the one about which we already talked. Then the so the only object on which this perversity takes a non-zero values, then the zero value is the just partition like n. And so L lambda for that lambda, well, maybe lambda 0. L lambda 0 is the the irreducibles are just irreducible representation of a symmetric group with a trivial action of the polynomial algebra. And so this is a C0, I mean, unless it's a sign, but let's assume we normalize things so it's a trivial. So the trivial representation, representation of Sn with 0 action of, well, x1, xn, y1, yn, where I introduce these coordinates so that sum of xi is equal to 0. Okay. And so so a little exercise that I think everyone can enjoy is that this L lambda 0 is a Pn object in other words, x from L lambda 0 to L lambda 0 is equal to cohomology of Pn. Now, so remember I told you, well, I didn't include it as a part of the theorem, but in this general motivational part, I talked about this local system of categories. So this is certainly very much present here. But so there is this loop when I go around 1 over n in positive direction, except that I went in negative direction for some reason. I go in positive direction. And then so monodromy is for this loop gamma. Monodromy for gamma is this Pn reflection at L lambda 0 in the sense of Hilbert and Thomas. But so what we want to do here is play a little bit different game and so there is also a, well, I like to call it Pn semi-reflection. And it means that I'll just construct, it's not an autoequivalence, but I just construct, so this Pn reflection is gonna shift. So it's characterized by the fact that L lambda 0 is going to go to L lambda 0 of 2n minus 1 to n, sorry. It's so I think it's actually Pn minus 1 object. So yes, and it's the function is identity on the quotient by this object, and so now I just construct a new T structure by which module the category generated by this is the same, but this thing, I mean, I shifted by the irreducible in the new T structure will be L lambda 0 shifted by n. So it will be T structure, and you and describe the projective generator and everything. Half a reflection of the whole. Okay, so yeah. So now let me explain my candidate for constructible realization, and it's kind of relates to different things, like geometric Lagrange or elliptic curve and elliptic hole algebras. But long story short, let me just give a precise definition. So so fix I, maybe for simplicity of notation, let me assume it's in 0, 1. And so I obviously lies in a unique in R minus 1 over N, R over N for unique R. And now I define MI to be the, so I fix an elliptic curve C and a degree N line bundle L0 on C. Okay. And MI will be the modular space of pairs, E phi, where E is a rank R vector bundle on C with determinant equal to L0. So this reflects the fact that my Hilbert scheme is centered. And phi is a section. And all these things are supposed to be theta stable, where theta inverse lies in my interval. And it's easy to see that it doesn't depend on this. So maybe I should remind, so the definition of stability for pairs, so it was, popular subject in the 90s. Yes, so it's theta stable if for any E prime in E, the slope of E prime is less than theta, and for any E prime in E such that E prime contains the image of phi, the slope of E prime, the slope of E mod E prime is more than theta. So this is what the stability means. Okay, so basically, briefly, is using the Lamont Greenfield construction. So Lamont construction, Lamont's 1987 paper, which was devoted to constructing automorphic sheaves on Ban N. Basically, not the theorem, but maybe the main diagram there of space. So one can define a functor from dB Koch. Okay, I'll write dB Koch X, although frankly, one has to work with the orbifold with this BKR thing. But in any case, one can construct a functor to the constructible derived category on bond prime on just this stack, parameterizing all such pairs if I forgetting the stability conditions. And so we can just restrict to this open subvariety in the stack. And so conjecture. So here, yeah, I should say that we take sheaves supported at 0. So conjecture that the heart of tau I goes to perverse sheaves on MI. Sending irreducibles to irreducibles. I mean, you can say fully faithfully. And so this would imply our conjecture. And so yeah, so this is unfortunately still conjectural, but we know kind of a lot and hope to give it another push and maybe prove it. But again, so maybe in -1 minute, I'll just give a quick example. And then I'll stop. So M, -1 over n, 1 over n is just, so the bundle has to have rank 1 and its determinant is fixed. So it's just projective space of H0 of L, which we can call P. So this is just a set of all divisors on the curve. And then we just do some obvious way to, if you start with a rep of Sn, you just produce a sheaf on the symmetric power. And then M 1 over n, 1 over n minus 1. Well, it's P of x1. So by Serre duality from L to O. So by Serre duality is just a dual space. And so from here to here, you can go by Rodon transform. And this is also essentially, well, here you have a Pn object, which is just a constant sheaf, and you get a half semi-reflection at this object. And then you can also look at this further things, and you get some very pretty geometry, which is actually related to geometry that, you know, was studied also by Michel at some point, and which was subject of Sasha Polishchuk's talk. So having to do with symplectic leaves of this Fagin-Odesky and Poisson structure. So basically, the point is that this P check contains the image of C under full linear embedding. And so this is like blow up. It's P check hat. So blow up of C. And on the further steps, so maybe I should stop writing, but you will blow up various second varieties. And indeed, you can see that these reducible objects, they will be like sheaf supported on the second variety. And so there's using a paper by my former student, Dobrovolska. I mean, one can check the conjecture maybe for these intervals. You know, things work out here. And generalizing it somehow, instead of the second varieties, you'll get some Harder-Nerasimhan stratas in this modular space of bundles. And you can also predict where this, you know, irreducible objects which shift non-trivially, where on which Harder-Nerasimhan strata they sit. And then Okay, I don't have time to talk about it, but this is kind of related to, I mean, there's this whole algebra and categorified whole algebra action. And for the part sort of corresponding to generators of a given slope, there is some nice, at least expected some nice relation between the action of corresponding generators and the T structure for the intervals with that endpoint. And hopefully this techniques will clarify it. But okay, so maybe I should